Welcome to The Explainer. Today, we are cracking open the machine learning toolbox to get you started with one of the most essential libraries out there, Scikit-learn. So here's the plan. First, we're going to bridge the gap between the dream of AI and the day-to-day reality. Then, we'll walk through your very first machine learning workflow piece by piece. We'll really dig into preprocessing, that's cleaning the data. From there, we'll check out the models, the actual learning engines. And finally, we'll cover how to tune those models and talk about what comes next on your journey. All right, let's jump right in. When we think about AI, we usually picture these super smart, futuristic robots, right? But the reality of machine learning, well, it's a lot less sci-fi and a whole lot more about rolling up your sleeves and getting your hands dirty with data. So the dream on the left here is this beautiful, simple process. You just take your messy, raw data, feed it into some genius AI model, and bam, it just figures everything out. But the reality on the right, well, that's where most of the work actually happens. A data scientist spends most of their time in that crucial middle step, cleaning, structuring, and preparing the data just so the model can even begin to understand it. And this really gets to the core of it. The AI pioneer Andrew Ng said it perfectly. Applied machine learning is basically feature engineering. And what's feature engineering? It's the art, really, of taking that raw data and turning it into meaningful inputs. We call them features that actually help the model grasp what it's trying to solve. This is exactly where a tool like Scikit-learn becomes your best friend. It is the go-to Python library for what we call traditional machine learning. So while other big libraries like TensorFlow are all about deep learning, Scikit-learn is your workhorse for pretty much everything else. We're talking data prep, modeling, evaluation. It's all there in one neat, consistent package. Okay, so what does this whole process actually look like in practice? Let's map it out. We can break it down into a really simple 4-step journey. This whole journey really boils down to 4 key steps. Step 1, you get your data. Step 2, you pre-process it. And yep, that's the feature engineering we were just talking about. Step 3, you pick a model and you train it on that nice, clean data. And finally, step 4, you have to evaluate it to see how well it actually did. Okay, but wait. Before we even think about training, we have to do something that is absolutely 100% critical in machine learning. We have to split our data. We take our data set and we break it into 2 piles, a development set that we use for building and tweaking the model, and a totally separate, untouched evaluation set that we'll use to test it later. This is non-negotiable, seriously. And here's why. The reason is actually pretty simple, but it's also really profound. If you test your model on the same data you trained it on, well, that's like giving a student the exam questions before the test. Of course they're going to get a perfect score. The model might just memorize the answers, not learn the patterns. And that gives you this false sense of confidence. The only way to get a true, unbiased look at how it'll perform out in the real world is to test it on data it has never, ever seen before. All right, let's zoom in on that all-important second step, pre-processing. This is where, to steal that phrase from Andrew Ng again, the real magic happens. The whole goal here is to get our data into a shape that the learning algorithms can actually work with. So, our mission, should we choose to accept it, is to turn chaos into order. Raw data, it's usually a total mess. You've got missing values, mixed up data types like text and numbers all jumbled together, weird outliers. It's just messy. Our job is to clean all that up and create a tidy, purely numerical, standardized data set that our model can finally understand. And listen, this isn't just about being neat and tidy for fun. It's crucial. A lot of powerful algorithms just plain assume that all your features are on a similar scale. So imagine this. You have 2 features. One is a person's age, right? Say from 0 to 100. The other is their annual income, which could be in the millions. Without standardizing, that income feature with its giant numbers would completely dominate the learning process. The model would pay way more attention to it just because the numbers are bigger. Standardization levels that playing field, so every feature gets a fair shot. And of course, Scikit-learn has a whole toolbox for this. The standard scaler is kind of your go-to, your typical starting point. If you need all your values squished into a strict 0 to 1 range, min-max scaler is the tool for you. Got text categories like USA or Europe? One hot encoder is how you turn those into numbers the model can read. And what if your data is full of crazy outliers? That's where the robust scaler comes in. It's built to handle that kind of mess and give you a much more stable result. Okay, our data is clean, it's standardized, it's ready to go. Now for the really fun part, choosing our learning engine, the model itself. So in supervised learning, most problems you'll encounter will fall into one of two main camps. On one side, you've got classification. This is where you're trying to predict a specific category, right? Like, is this email spam or not spam? On the other side, you've got regression. That's when you're trying to predict a continuous number, like the price of a house or what the temperature will be tomorrow. Okay, so let's say you have a classification problem. Which model do you even pick? Well, a great strategy is to always start simple. Use something like a logistic regression just to get a baseline, to see how a basic model does. If your data is more complex and can't be split by a simple straight line, then something like KNeighborsNeighbors might be a better bet. Dealing with really complex, high-dimensional data, support vector machines are incredibly powerful. And when you just need the best possible accuracy and you're not as worried about simplicity, a random forest is almost always a fantastic choice. So you've trained your model. It's spitting out predictions. But are they any good? How do we know? For that, we need metrics. Two of the most important ones are precision and recall. Here's a simple way to think about it. Precision is all about quality. Of all the emails your model said were spam, how many of them actually were spam? Then you have recall, which is all about quantity. Of all the spam emails that actually exist, how many did your model manage to catch? You see, it's often a trade-off between the two, and you really need to understand both to get the full picture of how your model is doing. Look, getting that first result is a huge milestone, for sure, but it's almost never the end of the story. In fact, it's usually just the beginning of the tuning process. This is where we try to tweak and adjust things to squeeze every last drop of performance out of our model. And the key to tuning is something called hyperparameters. The best way to think about them is like the knobs and dials on your model. These are settings that you have to adjust before the learning even starts. The model doesn't learn them from the data. So a perfect example is in the KNeighborsNeighbors model. That value K, how many neighbors to look at, that's a hyperparameter. You, the data scientist, have to pick the right number. So how on earth do you find the best settings for those knobs and dials? Well, Scikit-learn gives you some awesome tools for exactly this job. You've got grid search CV, which is basically the brute force method. It will literally try every single combination of parameters you give it. But a smarter and often faster approach is randomized search CV. Instead of trying everything, it just samples a bunch of random combinations. It's way more efficient and, surprisingly often, finds a result that's just as good, if not better. And believe me, the journey doesn't stop there. This is just the start. From here, you can do things like build pipelines, which let you chain all your pre-processing and modeling steps into one super clean workflow. You can explore more advanced metrics like the F1 score and ROC curves to get a much deeper understanding of your model's performance. You can dive into powerful ensemble methods like gradient boosting for a serious accuracy boost. You could even tune your hyperparameters faster with some really clever tools like having grid search CV. There is so much more to explore. So, at the end of the day, remember this. A model is just a tool. It's only as powerful as the data you give it. The real magic, the real genius, isn't in some complex algorithm. It's in understanding your data and taking the time to prepare it with care. And that brings us full circle, right back to where we started, feature engineering. Scikit-learn gives you this incredible toolkit to work with, but the story that your data gets to tell, well, that part is up to you. So what story will you tell? What problems are you going to solve?